Okay, so in this video I'm going to be doing another example of a second order differential equation using Laplace methods. So let's have a look. We've got d2x by dt squared minus 4x, you see that okay? Yep. Equals 24 cosine 2t. So we've got a second order non-homogenous differential equation. So let's first of all set the terms. So we've got the Laplace transform of x is going to be x bar. The Laplace transform of the first derivative, the x by dt, denoted as x dot. That's going to be s x bar minus x naught. X naught. Then we've got the Laplace transform of the second derivative, which is what we're interested in here, which is going to be s squared x bar minus s x naught minus x1. So let's imagine that we take the Laplace transform of the left-hand side and the right-hand side, split it up using into component parts by the principle of linearity, and then we're going to have the Laplace transform of d2x by dt squared, which is going to be s squared x bar minus s x naught minus x1 minus 4 x bar equals 24 of the Laplace transform of cosine 2t, which is going to be s on s squared plus a squared, in this case it's going to be 2 squared, which is 4. We're also told, by the way, that the initial conditions when t equals 0, x is going to be 3, and d2x by dt squared, we're going to need that as well. That's going to be, sorry, not d2x by dt squared, dx by dt is going to equal 4. Yeah, we don't need d2x by dt squared when t equals 0. We only need the derivative of the power that comes before. That makes sense. So if we're looking at the third derivative, we would only need the evaluation of the second derivative when t equals 0, kind of thing. So, so what we can do now, we can say that x naught equals 3 and x1 equals 4. So now we can rewrite this as saying s squared x bar minus s x naught, which is 3s, minus x1 minus 4 minus 4x bar equals 24s on s squared plus 4. So let's simplify this now. So we can say x bar s squared minus 4 minus 3s minus 4 equals 24s on s squared plus 4. Okay, let's move the paper up and let's keep going. So let's move the minus 3s minus 4 to the other side. So we can now say that x bar s squared minus 4 equals 24s on s squared plus 4 plus 3s plus 4. And I'm going to multiply that by s squared plus 4 on s squared plus 4. So we can now say that x bar s squared minus 4 is going to equal 24s plus 3s cubed yeah, 3s cubed plus 16 plus 4s squared plus 12s, all on s squared plus 4. So let's just simplify the algebra there. We say x bar s squared minus 4 equals 3s cubed plus 4s squared, 12s and 24s, plus 36s, plus 16, all on s squared plus 4. So we can now take the s squared minus 4 down here and say that. So now we have a non-reducible quadratic factor, the s squared plus 4. The s squared minus 4, we can actually reduce that even further. So we can say that x bar equals 3s cubed plus 4s squared plus 36s plus 16, all on s squared plus 4, s plus 2, s minus 2. And now we have something that can be reduced to a partial fraction expression. So let's go ahead and do that. So we can say that's going to be identical to as plus b on s squared plus 4 plus c on s plus 2 plus d on s minus 2. Now it's just a question of finding the coefficients of a, b, c, and d. And now we have the x bar in terms of its partial fractions. And now what we need to do is find the inverse Laplace transform of this. Sorry. So let's think about this. What does this look like? S on s squared plus 4. That looks like a cosine AT. Remember, we had the Laplace, the forward transform of cosine AT is s on s squared plus a squared, yeah? So we can rewrite this as saying x bar equals minus 3 times s on s squared plus 2 squared. And that looks very, very similar to cosine AT. And then we'll have plus 2, s on 1 on s plus 2. So we'll just take that out. 2, 1 on s plus 2, plus 4, 1 on s minus 2. And we can very easily see now that the inverse Laplace transform of this is just going to be x equals minus 3 cosine 2t plus 2e to the minus 2t plus 4e to the 2t. And that's the answer to d2x by dt squared minus 4x equals 24 cos 2t for the initial conditions of x equals 3 and dx by dt equals 4. And if you actually differentiated that twice to find d2x by dt squared, and then substituted that back into the original differential equation, that should give you the correct solution. So the magic of that was that you didn't need to worry about the particular solution, you didn't need to guess the particular integrals, anything like that. It just took care of itself, and there we have it.